So good evening, everyone. We will continue with our fifth chapter, Magnetism in Matter, for the third unit, Magnetic Effects of Current and Magnetism. Okay, for the class 12th physics. So till yesterday, we actually got into the entire, section of how we can, find the magnetic field for a bar magnet. We saw some similarities in the way we express the magnetic field for a bar magnet with that of what we had found for a solenoid in the previous chapter, okay, in chapter 4. And we also saw that, there is a correlation with the electrostatics phenomena. Okay, there are some comparisons that in the equations that we can derive for the magnetic field and the electric field. Okay, so we were seeing those, we had seen those aspects also. We also found out magnetic moment, and we also saw there's a relation between magnetic potential energy with magnetic moment and the magnetic field. So we had seen there was a little part of it that was left, that was the electrostatic analog between bar magnet. Like you can consider the bar magnet as a magnetic dipole with that of an electric dipole. Okay, so suppose we replace some of the terms with in the electric field, in electric field equations, like if we take, so suppose we substitute E with B, okay, and the dipole moment, electric dipole moment with the magnetic dipole moment, okay, and the constants that we use, that is 1, 4, pi, epsilon 0 with mu 0 by 4 pi. Okay, you can see very easily we can substitute all the terms that we commonly use for the electrostatics, okay, with equivalent, corresponding terms in magnetic field domain. Okay, so then we can, suppose we have the bar magnet with length L. Okay, so this is the length of the bar magnet. Okay, this is the length of the bar magnet, and suppose we are considering the magnetic field along the in the equatorial say equatorial plane. Okay, so suppose this is your bar magnet. Okay, I can actually draw it in the horizontal manner. It would be easier to understand. Okay, so if we have this as a bar magnet, okay, so the field along the axis of the bar magnet is actually the BA. Okay, and the if we're considering the field along the perpendicular to the bar magnet, okay, in the kind of equatorial section, then that would be B. Okay, so this is what we are calling BE and BA. So suppose we can write the equatorial field, the expression would be BE is equals to minus mu 0 m upon 4 pi r3. Okay, and similarly for your axial magnetic field, okay, the axial field would be mu 0 m upon, sorry, mu 0, this would be 2m, this 2m, okay, by 4 pi r cube. Okay, so you can see that there is an analogy between electric and magnetic, dipoles. Okay, we can get, a similar way of expressing the field for electric as well as your magnetic dipoles. Okay, magnetic dipoles. are analogous. Okay. Over here, you can see that, if you substitute the terms for electrostatics, you can get there are equivalent terms or variables in magnetism also. Okay, so with that, we'll move on to today's content. Okay, so now we will see magnetism and, how we can relate Gauss's law with magnetism. Okay, so over here, since we had seen, okay, so this is your bar magnet. Okay, this is your solenoid. The B is your solenoid, and this is your electric dipole. This is your, I'm just writing ED as the electric dipole. Okay, so in C, there are some, like when we had learned about Gauss's law, okay, we can, as per the Gauss's law, a closed surface, okay, can be represented by, over here we have two surfaces, okay, we are considering two surfaces. This is 1 and this is 2. Okay, so for the region 1, it can be, you can see that in this closed surface, the number of lines leaving the surface are equal to the number of lines entering the surface. Okay, and there is no net charge enclosed by the surface. Okay, the charges are here. Okay, so there is no net charge over here. Okay, the closed surface over here only has the electric field lines entering and exiting. Okay, and they are equal. For region 2, okay, there is a net outward flux because there is a net positive charge associated with the second region. Okay, now this is for your electric field. Okay, electric field for an electric dipole. Okay, but in the case of the say magnetic fields, okay, where we can consider a bar magnet as well as a solenoid. Okay, so it is different because we have continuous and the magnetic fields, actually the field lines, okay, the field lines are continuous. Okay, so field lines are continuous. Okay, and they form closed loops. Okay, so this you can see for figures A and B. Okay, and you can see that the regions 1 and 2, okay, with respect to both, they are actually showing you how the number of magnetic lines that are entering, that are leaving the surface, this region, okay, this region over here, as well as this region over here. Okay, so the number of lines that are actually leaving the surface is equal to the number of the lines entering it. Okay, so the magnetic flux in both the regions is actually 0, which is not the case for the electric dipole. Okay, over here there was no net charge. Okay, so there is no flux, but over here in region 2 there is a flux. Okay, there is a net outward flux because it has a positive charge. We are not considering any charges over here. Okay, so this is totally based. There is a current associated with the solenoid, and for the bar magnet, it's just there because of the existence of the magnetic dipole. Okay, so to prove or to understand the Gauss's law with respect to the the magnetism of bar magnet, we are going to consider, okay, a small area element del S. Okay, so this is your del S. Okay, and you have a magnetic field associated, with that del S. Okay, so this is your entire closed surface. Okay, this is your entire closed surface, and this is your del S. Okay, the small area element that we are considering. Okay, so over here we are going to associate, we are going to say that phi is the magnetic flux. Okay, we want to find out what is the magnetic flux. Okay, to understand, the passage of the magnetic field through this closed surface, and also to prove the Gauss's law that is associated with the magnetism. Okay, so the flux, okay, through this surface can through an area element, the small area element del S, can be given as del phi b. goes to B dot del S. Okay. So B is the field and del S is the small area element. Okay. So now what the net flux would be? Okay. Now this is for a small element. Okay. So we can find this del phi B for all individual small area elements. Okay. And then we can calculate the net flux as a summation of all these, individual small area elements. Okay, so this will be summation over all means that all the area elements of del S. Okay, all del S, you can just write it as that, is equals to all, okay, B dot ds. Now we know for we saw that when we are considering the magnetic field, okay, passing through a closed surface, actually the net flux is zero. Okay, we saw it in the previous slide also. Okay, so this is going to be zero. Okay, now if you compare it with the electric field Gauss's law, oh sorry, Gauss's law for electrostatics. Okay, so if we say Gauss's law for electrostatics, okay, so that actually gives us del E, sorry, summation of E del S. This is not going to be zero. This is going to be q by epsilon 0, where q is a charge that is enclosed by the closed surface. Okay, so this is a difference that we see with respect to the Gauss's law for electrostatics, and this is the Gauss's law for magnetism. Okay, so this is what we see for magnetism, and this is what we see for the Gauss's law for electrostatics. Okay, so over here that's why we can actually see that while the electrostatics is going to reflect that there is an electric charge enclosed by the surface. Okay, with respect to magnetism, this shows that isolated magnetic poles, okay, monopoles do not exist. Okay, so Gauss's law for magnetism again reiterates that no monopoles can exist. Okay, so this is what we see, and because there are no sources or sinks when when we are considering the magnetic field. Okay, and the simplest magnetic element, the magnetic element for electrostatics, we have a charge as the basic element when we are considering electrostatics. But for magnetic for magnetism, the basic element for magnetism is the dipole only. Okay, or as we have seen in the previous class, it can be a current carrying loop. Okay, so a magnetic dipole or a current carrying loop, okay, is the basic element for the magnetism. So finally, we can say, okay, that what would be the statement for the Gauss's law then? Okay, I'll just write it here. Gauss's law states that states that net magnetic flux through any closed surface is zero. Okay, this is with respect to magnetism. Okay, Gauss's law for magnetism. Okay, so this we have proved. Now we have been talking about magnetic field, magnetic dipole moment, okay, but the most fundamental example of magnetism that we see around us, or that we know does exist, is actually the earth as earth, the earth's behavior as a magnetic, as a bar magnetic itself, as a bar magnet itself. Okay. So Earth's magnetic field has strength of the order of 10 raised to minus 5 Tesla. Okay, and it varies from place to place. Okay, so if this is your Earth, Okay, so the magnetic field at the equator is actually going to be different from magnetic field at pole. Okay, so this the order of the variation would actually be 10 raised to of the order of 10 raised to minus 5. Okay, the variation. So previously, like we, it was not known how the magnetic field was generated. Okay, but with time, when there was more, studies done to understand the interior of the Earth. Okay, so scientists realized that that there is the formation of electric currents. Okay, in the outer core of the Earth, as we know that actually, as over here only, I'll just draw it. Okay, so this is your Earth's crust. Okay, then you have the mantle. Okay, and then you have the outer core, and then you have the inner core. So the inner core is actually solid, and the outer core actually is liquid. So due to the Earth's rotation, okay, there are convection currents that are forming in the outer core, in the fluid outer core. Okay, and because there is also it is composed of, the outer core is composed of, molten iron and nickel. Okay, so because of that, and because of the Earth's rotation, convection currents are forming in the outer core. Okay, and due to that, an electric current is set in the outer core due to this convective motion. Okay, so this method, or this phenomena, is actually called the dynamo effect, and this is the reason why we say that Earth's magnetic field exists. Okay. This is the recent, theory that we are considering as the origin of the Earth's magnetic field. Okay. Now there are some differences. Okay. Oh, like in general, if you just say that we already know that the Earth's axis is tilted. Okay, and we have a North Pole and the South Pole. Okay, but there is a difference in the geographic North Pole and the magnetic North Pole. Okay, so in this direction, you can see that you can have a magnetic equator, you can have a geographic equator, and similarly, you can have a geographic North Pole and geographic South Pole, and a geographic, and a magnetic South Pole and magnetic North Pole. Okay, so it is that is why we can say that the axis of the dipole does not coincide with the axis of rotation of the Earth. Okay, and the axis of the dipole is actually tilted at an angle of 11.3 degrees. Okay, you can see that this is the angle between the geographic, the geographic, or you can say the axis of the rotation of the Earth and the dipole. Okay, so now since you suppose this is your Earth, and the axis is already tilted. Okay, so this is your NG, FG, and then at an angle of say 11.3 degrees. Okay, so this is actually your north magnetic pole, and this is your south magnetic pole. Okay, and with respect to that, you can have the geographic equator, and with respect to this, you can have a magnetic equator. Okay, so there is a difference in both, and okay, so because we know that they do not coincide, there are the locations of the magnetic poles are different. Okay, so you usually what we consider this as to be, the geographic equator is 0 degrees. Okay, latitude, and the North Pole is like 90-degree latitude. Okay, so we can see actually that the North Magnetic Pole is at 79.74 degree north and 71.8 degree west, and the magnetic South Pole is actually at 79.74 degree south and 108.22 degree north. Okay, so you can see that there is a difference. Okay, it does not coincide. Over here, this diagram actually kind of shows you how the dynamo effect is kind of generating the magnetic field. Okay, so this is the outer core, this is the inner core, and these are the convection currents that are there. Okay, and fluid convection currents, and this is a magnetic field lines. Okay, that we see. Okay. There is also, understanding that usually when we had seen, a bar magnet before. Okay, so suppose this is a bar magnet. Okay, this is north and south. Okay, so previously we had seen that the field lines, okay, the direction of the field lines was different than what is shown in the diagrams over here. Okay. So, if you remember, the field lines are actually going out from the north and entering the bar magnet from the south. Okay. So, this was your closed loop. Okay. This was your kind of like, suppose one field line. But over here in this diagram, you can see, as well as in this diagram, that the field lines are coming in from the north and exiting from the south poles. Okay, over here also you can see that the magnetic field lines that is associated with the magnetic field of the earth, the direction is different than what we know of the bar magnet. Okay, so hence we can say that there is a difference. Okay, and what is that difference? The difference is that there is a convection that we follow. Okay, we call the magnetic north as the magnetic north pole. Okay, because the north direction of the magnetic needle actually points to the North Pole. Okay, so actually this nomenclature of where this is being called North Pole and this is being called the South Pole is actually because that when you freely suspend a magnetic needle, okay, so the north of this actually falls at the north magnetic pole, and the south of this needle is actually pointing towards the south. Okay, but we know that only unlike or different the different if you have the polarity is different, only then the attraction is there. Okay, so only unlike poles are going to attract each other. So generally in that sense we can see that actually the north is pointing towards the south of the it's actually the south of the field. Okay, the Earth's magnetic field, and the south tip of the magnetic needle is actually getting attracted to the north pole of the Earth's magnetic field. Okay, so that is why actually the dipole is kind of the magnetic dipole with respect of the Earth's magnetic field is actually different. Okay, than what we are denoting as the north magnetic pole and south magnetic pole. Okay, so in reality, the north magnetic pole actually behaves like the south pole of a bar magnet inside the earth. Okay, so this over here, the direction that is given. Okay, where this is going inside, this is actually so if we consider the earth as a bar magnet, this is going to be the south pole of the bar magnet and this is going to be the north pole. Okay, so south of Earth's magnetic field is actually the north magnetic pole, and the north of the Earth's magnetic field is actually the south magnetic pole. Okay, so this is something that we have to remember. Okay, so now we understood the how the Earth itself behaves like a bar magnet, and we could see how it can be visually represented. Okay, now since you already saw that the north magnetic pole and the geographic north, okay, so it can also be called as true north, okay, is actually uh, you know a bit different. Sorry, the geographic north and the north pole is a bit different. Okay, now suppose we are considering the earth. Okay, we all have heard that there is a 0 degree latitude, okay, that passes, sorry, 0 degree longitude, okay, that passes through, if you remember, Greenwich. Okay, so this is called the meridian. Okay, so this is your geographic meridian. Okay, so similarly, as we found a different kind of a magnetic poles also, we can get a different magnetic meridian also. Okay, so what is the magnetic meridian? It is a vertical plane which passes through the imaginary line joining the magnetic north and the south poles. Okay, so again, if we are considering this as the earth, okay, and we saw that this is your geographic north. Okay, this is your geographic south, this is your magnetic north, and this is your uh, magnetic south. Okay, so this line is going to be called the magnetic meridian. Okay, the line which is joining. Okay, now if we take a magnetic needle and we, just freely suspend it, okay, and it is left to swing in a horizontal plane. Okay, then it will actually lie in the magnetic meridian. Okay, and the north pole of the needle will point towards the magnetic north pole. Okay, and the south of the needle is going to point towards the south magnetic pole. Okay, or magnetic south pole. Now, the line that is joining this magnetic pole is actually tilted with respect to the geographic axis of the earth, as we can see. Okay, this is your geographic axis. Okay, this is your geographic axis. Okay, and this is your magnetic axis. So there is an angle between that. Okay, so now this angle that is made between the geographic meridian and the magnetic meridian is called the magnetic declination. Okay, so as you can see, the angle between the two geographic north, okay, and the north shown by the compass needle is called the magnetic declination. Okay, so this you can see also over here in like a 3D space. If you see, this is a geographic north, this is your magnetic north. Okay, so the angle over here is called alpha. Okay, so alpha is actually the so this alpha is actually the declination. Okay, now there is another uh, element or term which is associated with Earth's magnetic field. Okay, so now if we consider a magnetic needle is perfectly balanced about a horizontal axis. Okay, so this is your horizontal axis and the needle is balanced in this horizontal axis. Okay, and it can swing in the plane of the magnetic meridian. Okay. Now, if it is, balanced about the horizontal axis and it can swing in the magnetic meridian, okay, it will make an angle with the horizontal. Over here, you can see that there is a horizontal component of the field, and this is the magnetic field. Okay. So this angle that it makes with the horizontal of the earth, horizontal surface of the earth is actually called the inclination. Okay. So now if we consider, okay, that the angle between DBE and angle, okay, between DE and HE is actually I. Okay, this is your inclination. Okay, over here, suppose we, consider this point P, okay, on the Earth's surface. Okay, and this is also the magnetic, meridian. This is the magnetic meridian, the plane, okay, at P. The plane is actually, you can consider it as a, section that is cutting through the earth. Okay, so the total field at P can be resolved into obviously a horizontal, component and a vertical component. Okay, this is your magnetic field at P, and it can be, kind of it can be resolved into two components, horizontal and horizontal and the vertical. Okay, and in 3D you can see that this is actually the vertical component and this is the horizontal component. Okay, this is the true north and this is the east. Okay, when we are considering on this is the earth surface. Okay, this is on the surface. So the angle between BE and HE is actually the inclination, the dip. Okay, I. So So then hence we can say that to describe the magnetic field of the earth at any point on the earth's surface, we need three quantities. Okay. So one is the declination B, the other is the angle of dip or the inclination and the horizontal component of the earth's field. Okay. Then we can find the vertical component uh, of the magnetic field at any point on the earth's surface. How we can find that out is using trigonometric relations. Okay, so from the diagram, okay, from this diagram you can see that ZE is actually BE sine of the inclination angle. Okay, and then HE is actually BE cos of the inclination angle. Okay, so to find the inclination angle, we just need to know the vertical component and the horizontal component, and its ratio is going to give you the inclination angle. Okay, you can get the tan, use the tan inverse, and you can find the inclination of the magnetic field at any point on the Earth's surface. Okay, so this is how we describe the Earth's magnetic field in terms of different components. Now we come to a few other phenomena that is associated with magnetism. Okay, so you have magnetization and magnetic intensity. Okay, so we have a lot of materials. Okay, a lot of materials which are showing magnetic properties. Okay, so you have two such properties. One is magnetization and the other is magnetic intensity. Okay, so we have already seen in the last chapter, okay, that a particular substance can have inherent magnetic moment. Okay, and that was due to the circulating electron in an atom. Okay, we saw that the charge is moving, and due to the movement of the charge, a magnetic field is generated, and the atom itself can act as a magnetic moment because of that. Okay, so in a bulk material, obviously the magnetic moment of each atom is going to add up and we can have a net magnetic moment. Okay, so that is going to be non-zero. Okay, so there is going to be some magnetic moment associated with the bulk material. Okay, which has a lot of the atoms which are acting as magnetic dipoles. So the term magnetization, okay, of a sample can be defined, okay, as the net magnetic moment per unit volume of that material. Okay, so we can write it as M is equals to M net, okay, net magnetic moment upon the volume of the material. M is equals to M net by volume. Okay, and we can see that there is the magnetic moment is associated with magnetization. So there is going to be the direction. So that is why M is a vector. Okay, and the dimension is going to be length inverse and ampere. Okay, so the unit of magnetization is ampere per meter. Okay, now to understand how magnetic field can be associated with this magnetization, we will consider a long solenoid of again n turns per unit length, and it is carrying a current I. Okay, so we will try to find the magnetic field that is existing inside the solenoid. Okay, so previously we had seen, okay, in the previous chapter that B0 is equals to mu 0 n I. Okay, this is what we know. Okay, now we are considering this as the we know mu zero is actually the permeability of free space. Okay, this is with respect to free space. Suppose the solenoid is now filled with a material with non-zero magnetization. Okay, over here we were considering vacuum. Over now we are considering that the solenoid, the interior of the solenoid is filled with a material with non-zero magnetization. Okay, so now the field inside the solenoid will be different. Okay, so that sorry. So the field now, okay, B is going to be greater than B0 because now we have a non-zero magnetized material. Okay, so the total field that the net field or the total field that we see would be an addition, a sum of the, B0 and Bm. Okay, so and Bm can be given as mu0 m. Okay, so sorry, this is permittivity, not this is the permittivity. Sorry, okay, of free space. Now over here again, you can see that when we are trying to find Bm, okay, mu0 is constant. Okay, it's the same as the permittivity of the vacuum. Okay, with respect when we try to find it, the magnetic field. Okay, now we will introduce another vector field called magnetic intensity. Okay, that is denoted by H. Okay, so since over here we saw, that there is, we are introducing another material, okay, with non-zero magnetization, we are going to define magnetic intensity, okay, that exists because of the solenoid, okay, that is filled with the material now as H is equals to B by mu 0 minus M. Okay, H dimensions are same as the M dimensions. Okay. So both their units is actually ampere per meter. Okay. Then we can write the total field as B is equals to mu 0 H plus M. So you can see that the total magnetic field, okay, with respect to the solenoid that we have considered is actually a function of both the intensity and the magnetization of the material that is being used. Okay, and then we can see that hence the total magnetic field can be separated by into two parts. One is obviously the intensity H, okay, and then you have M. Now this M actually depends on the magnetic material that we use. Okay, depends on the magnetic material that we are using. Okay, so now we are going to introduce another term, okay, which is a measure of how a magnetic material responds to an external field. Okay, so that means how susceptible a material or a substance is to get magnetized. Okay, so that is actually expressed as M is equals to chi H. Okay, so chi is the quantity which is a measure of how a magnetic material responds to an external field or how easy it is for the material to get magnetized. Okay, and it is called magnetic susceptibility. Okay, if if your chi is positive, it is a paramagnetic. Okay, if your chi is negative, it is a diamagnetic. We will see what these paramagnetic and diamagnetic, terms mean. Okay, so we can say that the magnetic field, that is produced due to suppose a bar magnet is going to depend on the magnetic intensity as well as the magnetization of the material that we are using. Okay, so inherently, after we have introduced this another term called chi, we can write the magnetic field as mu 0 1 plus chi h. Okay, and if we simplify it more, it can be mu r H is equals to mu H. Okay, so what is mu R? Mu R is actually the relative magnetic permeability. Okay, so this is magnetic permeability, mu R. Okay, and it is similar to how we were using dielectric constant in the electrostatics. Okay, and mu is actually this mu is related to the material or the substance that we are using. Okay, so this can vary with respect to the substance we use. Okay, so we can write mu as mu, that is the actually magnetic permeability. Okay, mu R is relative and mu is the magnetic permeability of the substance that we are using. Okay, and we can get it as mu 0 mu R. Okay, and again 1 plus that. So if you know the magnetic susceptibility of the material, and obviously we know mu 0, okay, we mu 0 is actually equal to 4 pi into 10 raised to minus 7 Tesla meter ampere. Okay, so this is what we know, and if you know, and if experimentally we have found out chi for the material, we can find mu. Okay, so we can say that the three quantities are interrelated and only one of them is independent. Okay, so this is your independent. Okay, so if one is given, you can find out the other two. Okay, so now we come to the magnetic properties of the materials. Okay, so now we talk about the magnetic properties of the materials. Okay, so not all materials are going to be, they will not have similar behavior with respect to how easily they can get magnetized or what is going to be their magnetic properties. Okay, so in this table, okay, we can see a correlation of the different, terms that we use. Okay, so you have chi, you have mu r, the relative magnetic permeability, and you have the magnetic permeability, and this is a magnetic susceptibility. So this you can see how the values range, okay, with respect to the three different, magnetic materials. You have diamagnetic materials, you have paramagnetic, and you have ferromagnetic. Okay, so what are diamagnetic materials? Okay, so these have the tendency to move from stronger to weaker part of the external magnetic field. Okay, so actually what is going to happen is that uh, this will actually repel. Okay, so usually magnet attracts metals like iron. Okay, this would repel a diamagnetic substance. Okay, so and they have almost they have negative magnetic susceptibility. You can see chi is equals to mu 0, and the relative magnetic permeability is also 0 for it. Okay, and actually no, this is actually for materials like superconductors. Okay, so sorry, this is for superconductors. Okay, we see these relations where the magnetic susceptibility is negative and the relative magnetic permeability is 0. That is for superconductors. Okay, so they have perfect conductivity and perfect diamagnetism. Okay, so in a simple way, we can see how diamagnetism actually happens is that electrons in the atom are actually orbiting around the nucleus and they have orbital angular momentum. Okay, this we saw even in the last chapter. Okay, and obviously this is going to correspond to, suppose we have a current carrying loop. Okay, and it will have a magnetic moment. Now, diamagnetic materials actually, occur when the resultant magnetic moment is the atom that we are considering is actually 0. Okay, so when the magnetic field is applied, the electrons having the magnetic moment in the same direction will slow down and those in the opposite direction will speed up. Okay, this is in accordance with the induced current and Lenz's law. Okay, we are not going to deal with it over here. But the general rule is that the substance, okay, the diamagnetic substance, okay, the net moment magnetic moment is in opposite direction to that of the external magnetic field. Okay, so we are going to the applied field or the external magnetic field. Okay, since the net magnetic moment is in the opposite direction, so it will repel. Okay, so it will repel the magnetic field that is there. Okay, so some examples are bismuth. Okay, then you have copper, and you have lead, you have silicon. Okay, so these are some of the examples of diamagnetic substances. Then you have paramagnetic substances. Okay, so they are substances which can get weakly magnetized when they are placed in an external magnetic field, and they have a tendency to move from a region of magnetic field to strong magnetic field. Okay, so in this case, what happens that the individual atoms, or if you're considering ions or molecules of these paramagnetic materials, they will have a permanent magnetism. Okay, sorry, they will have a permanent magnetic dipole. Okay, so for paramagnetic, so there is going to be, there is a magnetic dipole moment. So M exists. Okay, M exists. Okay, and if we are considering an external field BXT, okay, which is strong enough even at like lower temperatures, the individual magnetic dipole moment can, align. So the M aligns, so the M aligns in the same direction as the uh, BXT, aligns with respect to the external field. Okay, now since if they are aligned, then there is going to be a a magnetic field, and it is not going to repel the external magnetic field, it will be attracted. Okay, and so, and the if you place it in a uniform field, then the field is enhanced. Okay, and if you have a non-uniform magnetic field, okay, but the external or the applied field is non-uniform, then the bar, the magnetic, the bar magnet made up of the paramagnetic material is going to move from weak field to stronger field. Okay, so some materials are aluminium, sodium, calcium, oxygen at standard temperature and pressure. Also, copper chloride as a molecule. Okay, so with experiments, people have found that the paramagnetic material, okay, the magnetization of such materials is actually inversely proportional to the temperature. So if you increase the temperature, your magnetization is going to, reduce. Okay, so at low temperatures, magnetic but paramagnetic materials can get magnetized. Okay, so we can write this as CB0T. Okay, so C is actually the Curie's constant. Okay, so to continue on the magnetic properties of materials, so we have three types of materials. We have diamagnetic, paramagnetic, and ferromagnetic. Okay, so all of these have some relation with respect to the magnetic susceptibility, as well as the permittivity. Okay, sorry, this is the permeability. Okay, and you have relative permeability, and you have the permeability in free space. So for diamagnetic substances, these actually tend to move from stronger to weaker, part of the external magnetic field. And uh, so usually for a diamagnetic substance, okay, so the when it is placed in a non-uniform magnetic field, okay, so the magnetic, say a bar magnet, it will try to move from high to low field. Okay, so you can see that the magnetic susceptibility is in the negative region. Okay, and your permeability, relative permeability, and the permeability of the material itself is much lower, the values. And a bar magnet, okay, which is made up of a diamagnetic material, it will not, attract, it will repel the diamagnetic substances. You can also see it in the in this figure. Okay, this is the behavior of the magnetic field lines near a diamagnetic substance. Okay, so usually we have some materials, those are called superconductors. Okay, so these are diamagnetic in nature. And for perfect superconductors, the magnetic susceptibility is going to be -1 and the relative permeability is going to be 0. Okay, and usually in diamagnetic substances, the resultant magnetic moment is like 0, and that is why when the magnetic field is applied, the electrons which have the orbital magnetic moment in the same direction will slow down, and those in the opposite direction will speed up, and due to this combination, the net magnetic moment becomes 0. Okay, and the net and even if it develops, like when it develops a very weak magnetic field, the net magnetic moment is going to be in the direction opposite to the applied field direction. Okay, and that is why there is a repulsion that is there. So this is your diamagnetic material. Then you have the other substance that is called the paramagnetic substance. Okay, so these do get magnetized. Okay, whereas diamagnetic minerals, it's very difficult to magnetize them, and so paramagnetic will get weakly magnetized. Okay, when it is placed when they are placed in the external magnetic field, and usually they move from a region of weak magnetic field to stronger magnetic field. Okay, that is why they get attracted to a magnet, but the attraction is very weak compared to with what we will see for the ferromagnetic one. Okay, so you can see the behavior of the magnetic field lines in the diagram over here. Okay, so their magnetic field lines are there. Okay, so they are not totally, the magnet does not totally repulse. Okay, repulse the, or it's not a repulsion that is seen between the applied field and the paramagnetic bar magnet. Okay, now this paramagnetism, the behavior, okay, or the characteristic of the paramagnetic substance, okay, it is also dependent on the temperature of the substance, or okay, so it also depends on the uh, thermal rotation or thermal motion of the atoms, and at a certain temperature, there could be no magnetization. Okay, so in the presence of say an external field, okay, which is strong, and at lower temperatures, the individual atomic dipole moments will can be will be made to align and point in the same direction as the external field. So you can see that there is a temperature dependency. Okay, and this temperature dependency can be explained by something called Curie's law. Okay, so where your magnetization is inversely proportional to the temperature. Okay, this temperature is actually the absolute temperature. Okay, so this is T is the absolute temperature, and you can see that you can write it as M is equals to C B0 by T. Okay, so B0 is your external field that is being applied. C is your Curie's constant, and then there because if magnetization is is dependent on these on temperature, your magnetic susceptibility will also be dependent on the absolute temperature. So in place of B0 over there, so you put your permeability over here. Okay, so if your external field is increased and your temperature is lowered, your magnetization will increase. Okay, and it will increase up to a certain level that is called the saturation point. Okay, so this is the magnetization at the level of saturation, and beyond this, the Curie's law becomes invalid. Okay, so this is the saturation value at after which your Curie's law will be invalid, as in that if you reduce your temperature too much, or you increase your external field a lot. Okay, so a certain value is reached that is above the saturation value, and then your Curie's law is not going to work anymore. Okay, so this is the paramagnetic substance. Now, if we come to the ferromagnetic, okay, so for ferromagnetic are the ones which get very strongly magnetized. Okay, these are actually the kind of permanent magnets that we create. Okay, so when such substances are placed in external magnetic field, okay, they will move from a region of weak magnetic field to the stronger magnetic field. Okay, and that is that they are strongly attracted to a magnet. When the external field is removed, okay, so these don't lose the magnetism. Okay, so the magnet, not all, but most, like some of the ferromagnetism, there is one called magnetite. Okay, so that is one of the minerals where the magnetization will persist. Okay, so what is the reason behind this? Is that the individual atoms, okay, or say ions or molecules that are present in the ferromagnetic material, okay, they already have a dipole moment. Okay, just like we had it in the paramagnetic material. But when they are interacting with one another, okay, so they will automatically align themselves in the direction of there are going to be zones, okay, of all the atoms kind of aligned in certain directions. Okay, so these are called domains. You can see over here. So all the atoms in this region will be aligned in this direction, then in this direction will be in this direction. Okay, so these are all the domains. So when you are placing it in the or you are applying an external magnetic field, okay, so the domains will start orienting themselves in the direction of the external field. Okay, so when they are all the domains start orienting themselves in the direction of the external field. Okay, so all the domains will kind of merge together, and they will grow in size. Okay, so these domains and the motion of kind of the motion where they're aligning themselves is the is present. There's a motion that is present when they're aligning themselves in the direction of the external magnetic field. Okay, so when this happens, okay, so they are all these domains, okay, there are numerous domains there. All these will then combine and form one individual large domain. Okay, and this is called a single giant domain. So usually the field lines, as we saw in paramagnetic, okay, so in paramagnetic they are present but they are not very concentrated, but for ferromagnetic material they are highly concentrated. Okay, similarly then what happens is when uh, suppose you remove the external field, okay, in which all these domain orientation, the direction orientation will happen. Okay, these some will, the magnetize for some paramagnetic minerals, the magnetization will stay. Okay, it will not disappear. Okay, and these are called hard ferromagnets. Okay, so hard ferromagnets. So you have your iron, aluminium, nickel, cobalt, copper. Okay, these are when these are all together, they form an alloy that's called alnico. Okay, so this is a hard ferromagnet. And for some, the magnetization will disappear when the external field is removed. So soft iron is one such material. Okay, and these are called soft ferromagnetic materials. So you can have, say, there are, ferromagnetic materials in its sense are, you have iron, Okay, we all know that iron is a very, we use bar magnets, okay, made up of iron or alloys of, iron. Then you have cobalt, and then you have nickel. You also have gadolinium. Okay, so these are all examples of ferromagnetic minerals. Okay, again, we have a temperature dependency, where because of temperature, a ferromagnetic material can, transition from being a ferromagnetic to a paramagnetic material. Okay, so the temperature of this transition where the ferromagnetic materials, will start losing their ferromagnetic property and, turn into paramagnetism and eventually probably lose the entire magnetism. Okay, so that temperature is called Curie temperature. So you have, Curie temperature varies with the kind of material that we use. You can see over here, cobalt has, a high Curie temperature. Iron also has a high one. Gadolinium has comparatively lower Curie temperature. Okay, so your magnetic susceptibility is, varying with respect to the temperature and the Curie temperature. Okay, so these are the examples of the different types of uh, say material that we have which show magnetic properties. Okay, so for some you can induce the magnetization, and when you remove the applied field it will lose, or for some it will persist. Okay, now we come to magnetic hysteresis view. I will just try to. Okay, so what is a magnetic hysteresis view? Okay, so there is a relation between B and H. Okay, and this is non-linear. Okay, for most cases, and this is a non-linear. And uh, how we can describe this is actually called the magnetic history of any sample that we are taking. Okay, so for say a one cycle of magnetization, there are different behaviors that the sample actually follows. Okay, so at O, okay, we have a non-magnetized sample. Okay, when the magnetic field is, applied. Okay, and suppose we are considering for this, we are going to consider an, unmagnetized, unmagnetized, magnetized core of, which is put in a solenoid. Okay, so when it is put in the solenoid, your current in the, passing through the solenoid is increased gradually. Okay, and when then we measure the magnetic field, okay, as well as the intensity. Okay, your magnetic intensity H, and we also measure your magnetic field. Okay, so we when the current is increased, your magnetic field, okay, keeps rising. Okay, you can see this blue line. Okay, so it follows this path. It will reach up to a value, okay, where it saturates. Okay, after this, even if you increase, this will continue to be in this value only. Okay, so this is from O to A. Okay, so the point O to A is where your magnetic field keeps rising and it saturates. Okay, this behavior actually represents the where the domains of the material is actually emerging, and the alignment is kind of shifting in the applied field direction. Okay, and the domain is growing, and after a certain point there is no increase. Okay, now we will try to reduce the H. Okay, from here we start reducing our magnetic intensity. Okay, when we start reducing the magnetic intensity, okay, and we will do it up till we reach 0. Okay, now at this point the magnetic field that is present, okay, so that we can denote as Br, which is the remanence. Okay, Oh, sorry, I think yeah. Okay. So this BR is actually, I do BR is remnants. Okay, so where you can see BR is remnants at point B. Okay, so this is also the remnant magnetism. Sometimes this kind of stays in the sample and you can measure it, how much is the remnant magnetism also. Okay, or you can also say how much is retained. Okay, so retentivity is also one of the terms that is used. So now the domains are still kind of aligned in the external field. Okay. Okay, so like they are not completely, they have been, they do not assume that random form that usually they have in magnetized state. Okay, so they still have some kind of, the domains are still remaining in the orientation of the external magnetic field. But now since you saw that we have removed the external driving field. Now what we do is from say B to C segment, okay, I is kind of reverse in direction. Okay, so say from O to A you have I in one direction. Okay, so B to C we reverse the direction. So what happens then is that the sum of the domains in the material will be flipped. Okay, so current the direction is increased. The direction is reversed. Okay, and the current is increased again. Okay, so again we will see that the the some of the domains that are there, okay, they will be they will start flipping. Okay, and the net field inside then becomes zero again over here at C. Okay, your B is equals to 0. Okay, this is done until you reach a point where your B becomes 0. Okay, so this is represented as we saw from by the curve BC. Okay, and this can also be called, okay, so this point can be denoted as HC because you see that there is a value in the H axis HC. So this is called the coercivity. Okay, why also it is mentioned. Okay, so this is coercivity. Okay, this point. Okay, the value of H at point C is called coercivity. Okay, now the reverse current is again increased in magnitude. Okay, and when you see, okay, so this is kind of, the opposite of this. Okay, this curve is, kind of like a mirror of this curve, but it's in the, opposite direction. Okay, so again you increase the current, okay, until a point where you get a saturation. Okay, so at point D, you again get saturation. Okay, so the curve CD is depicting this, this kind of increase in the current. Okay, and in the negative value. Okay, so the B is also increasing in the negative value. Again, we reach a point, or you can call it as Bs. Okay, so this is the saturated magnetic field. Okay, saturated magnetic field. Okay, now the current is reduced. Okay, from D to E. Okay, your I is then reduced. Okay, D to E, and then again reversed. Okay, from D to E, your I is reduced, and it is still in that the this direction. Okay, now after E, again your I is reversed in the original, in the starting, how the current direction that was followed for OA. Okay, so I is again reversed. Okay, and the cycle repeat itself, but you can see that now from here to here. Okay, so this is another curve that is going to be followed. Okay, and slowly you will, if you keep on, increasing your cycles of this magnetization, okay, the nature of the curves is going to be same. Okay, but these original traces are not going to be followed. Okay, so if this is your second cycle, if you go for a third cycle, so maybe it will start from here. Okay, but it will reach the same magnetic saturation point. Okay, it will reach the same magnetic saturation because this will depend on the material. Okay, okay, then again this. Okay, so this is how we can understand the history of magnetization, okay, of a material. And so we can say that for a given value of H, okay, your magnetic field B is not going to be unique, but it depends on the history of magnetization of the sample. Okay, so this is called the hysteresis. This phenomena is called the hysteresis. Okay, so this is actually, there is a lag that is left behind. Okay, there is a lag or there is a gap between the consecutive cycles that we see of magnetization. Okay, so this is the end of the magnetism and matter chapter.